Welcome to This Explainer. Today, we're diving headfirst into the invisible world of molecules to understand how their microscopic chaos creates the macroscopic world we feel every single day. Have you ever wondered why a balloon expands, or what temperature actually is on a physical fundamental level? Well, we are going to build the architecture of that chaos right from the ground up.
Here's our roadmap for today. We'll be hitting rules of the invisible, uncovering gas pressure, collisions and speeds, sharing the energy, and finally, ideal versus real gases.
Section 1. Rules of the Invisible. The Micro-World Foundation.
To actually make the math work here, physicists had to dream up a perfectly idealized model. Just picture gas molecules as perfectly elastic, rigid billiard balls. They're constantly zipping around in straight lines, smashing into each other. But, and here's the kicker, they never lose a single drop of kinetic energy. In this ideal setup, their physical size is literally practically zero compared to the massive voids of empty space between them. No attraction, no repulsion. They just move, crash, and bounce.
Moving on to Section 2. Uncovering gas pressure, from microscopic bounces to macroscopic force.
What's genuinely fascinating here is how we can take all that microscopic chaos and, well, box it up. Imagine just one single molecule bouncing around inside a perfect cube. Because we're assuming the walls and the molecules are perfectly elastic, we can mathematically track its exact velocity and momentum every single time it strikes a wall and rebounds.
Let's break down the actual mechanics. A molecule with mass m slams into the wall at velocity u. That gives it a momentum of mu. It bounces straight back with the exact same momentum, just in reverse, meaning the total change in momentum is 2mu. Now, by taking that momentum shift from just one single microscopic bounce and scaling it up to the literal billions of collisions happening every second, thanks to Newton's second law, we can calculate the total continuous force acting on that wall.
And that brings us to this incredibly elegant equation. The final result of all those tiny impacts, total gas pressure, P, is simply 1/3 of the gas density, represented by the Greek letter rho, multiplied by c squared, which is the mean square velocity of all those molecules. It's a beautiful piece of math that directly links the invisible, blinding speed of atoms right to the physical pressure pushing out on a container.
So why does this matter? Well, the crucial takeaway happens when we connect that pressure equation to the perfect gas law. Look at this. The average kinetic energy of a molecule is directly equal to 3/2 kT, where T is absolute temperature. Think about that for a second. That means the temperature you physically feel on your skin, it's literally just a direct measure of raw microscopic speed. Temperature is kinetic energy.
Section 3. Collisions and speeds, the chaos quantified. With billions of these invisible spheres zipping around at blistering speeds, bumping into walls and each other, you gotta wonder, how far can one actually travel before crashing into something? We call this elbow room the mean free path, represented by the Greek letter at lambda. First deduced by Clausius, it's just the average distance a molecule manages to fly before collision inevitably knocks it off course.
To actually calculate this, physicists use a pretty clever trick. Imagine drawing a theoretical cylinder of space based on the molecule's diameter and its speed over exactly 1 second. By doing this, we can figure out exactly how many other molecules it is mathematically guaranteed to hit. The logic is simple. The wider the molecule, or the more densely packed the gas, the shorter that mean free path becomes. Makes perfect sense, right?
But there's a bit of a catch here. Not every molecule is moving at the exact same speed. Some are dragging along, while others are absolutely flying because of constant random collisions. Enter Maxwell's beautiful bell curve. This graph maps out the statistical distribution of velocities within that whole chaotic mess. The area under the curve represents all the molecules, and that peak, that shows where the vast majority of the speeds are clustering.
Now, let's look at the math here, because it's actually slightly counterintuitive. Thanks to the asymmetrical shape of Maxwell's curve, we end up with 3 distinct ways to define average speed. Surprisingly, the most probable speed, the absolute peak of the curve, is actually the slowest of the 3. Next up is the simple mean average speed. And finally, the fastest is the root mean square speed, which, by the way, carries the most mathematical weight when we're calculating kinetic energy.
Section 4. Sharing the energy, degrees of freedom.
We know these molecules have kinetic energy, right? But how do they actually store it? Well, it depends entirely on their physical shape. This brings us to a concept called degrees of freedom. Essentially, these are the independent ways a molecule can move through space or spin around. Physicists use the formula F equals 3n minus r to calculate this, basically looking at the number of atoms in a molecule, n, and the rigid bonds holding them together, r.
You can clearly see how this plays out in the real world. A monoatomic gas, something like helium, is basically just a single dot. It can only move up, down, left, right, forward, and backward. That's 3 degrees of freedom. But a diatomic gas, like oxygen, it looks more like a dumbbell. So it can translate through space, but it can also rotate in 2 different directions, bumping it up to 5 degrees of freedom. Polyatomic gases have even more. This structural difference fundamentally changes a gas's specific heat ratio, its gamma, which dictates exactly how it absorbs heat.
And here's where nature shows its absolute love for perfect balance. The principle of equipartition of energy states that when a gas reaches thermal equilibrium, its total energy doesn't just pile up in one type of movement. No, it gets distributed perfectly equally among every single available degree of freedom. So, exactly 1/2 kT of energy goes to moving left and right, exactly 1/2 kT goes to spinning, and so on across the board.
Section 5. Ideal versus real gases. Breaking the rules.
So far, we've built this incredibly pristine, perfect mathematical architecture of chaos. We've assumed point-like molecules that never, ever attract each other. But do gases actually play by these perfect rules in the messy reality of the physical world? What happens when we compress them so intensely, squishing the molecules so close together that they're on the literal brink of turning into liquids? To answer that, we've to talk about Thomas Andrews' famous experiment on carbon dioxide. He specifically designed this test to map out exactly where these ideal gas laws, specifically Boyle's law, completely break down under extreme, crushing pressure. To pull this off, Andrews used a highly specialized piece of gear. He forced carbon dioxide and dry air into tiny glass capillary tubes, sealed them up with mercury, and then applied massive pressure using these heavy-duty manual screw plungers. By doing this, he could carefully track their volumes at varying, tightly controlled temperatures. The curves he mapped out from this data are known as isothermals.
And his results? Honestly profound. He found that, sure, at really high temperatures, gases behave pretty ideally. But the very second these real gases near liquefaction, when the temperature drops and the pressure is extreme, they deviate massively from the math. Those perfect billiard ball rules we talked about, they go right out the window. Why? Because in reality, molecules do take up physical space, and they do exert subtle attractive forces on each other when they're shoved close enough together.
So, as we wrap up this explainer, I want you to consider this. The kinetic theory of gases isn't just some abstract mathematical exercise. By calculating the exact speed, the degrees of freedom, and the mean free path of utterly invisible molecules, we gain the power to predict phase changes and master thermodynamics. If understanding microscopic chaos lets us do all that, what entirely new, mind-bending macroscopic materials are we going to engineer next? Thanks for exploring this architecture of chaos with me. Keep wondering and keep learning.